Kia ora Year 13 and Year 12. This video is going over how to differentiate exponential functions. So it pretty much goes along with Delta Chapter 1503 in the new version and Chapter 6.3 in the old edition of the textbook. So what I wanted to do is to start by just reviewing what the graph of y equals e to the x looks like, and then looking at how we differentiate it. So this is one of the most special functions in maths. This is the graph of y equals e to the power of x. Now e is an irrational number. It's 2.7 point blah 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 blah, and we leave it as an exact value when we write it as e. So it's a lot like pi in that sense. The reason it's so special is that if I take the gradient at any point on this graph, and we can see this pretty easily, or roughly see it pretty easily. I'm hoping this graph is to scale. So let's look at the slope of that line, of the tangent to the curve, roughly here. This will just give us a feel for it. Now I haven't drawn it at exactly the right spot, but you can see that I've got x equals 1 here, and the gradient of the curve here, so the steepness of this tangent line, is 2.7 blah blah blah. In other words, when we differentiate e to the x, we get e to the x. So the gradient is equal to the value of the function. So what am I blathering on about here? Well, when x is 1, the value of the function is e. And that's the same as the slope of the tangent at that point. And this makes the exponential family extremely useful to us in lots of real-life mathematical applications. You'll see this later on in the course when we look at integration and differential equations. Being able to change things into functions where we've got e to the x makes a whole lot of stuff easier. And you're going to see that when we get differentiating. So the basic question you're never going to get asked in a level 3 calculus exam. Suppose we've got f of x is e to the x. Find me the derivative of it, because you're going to be given that on your formula sheet. But we are often going to have to use the chain rule to work with exponential functions. So what I want to look at now, if I can get the right window back, is just 6 questions that are similar to the ones in Delta, and all of them are going to use the chain rule. So let's do just one the long way with the chain rule, and then I'm going to switch to doing the inside and the outside function method that I went through in my last video. So suppose that I've got the following function. Y is equal to e to the power of x squared. So this is a function of x. This is going to be my inside function. dy by dx is equal to dy by du times du by dx. So what's u? Well, we've got y is equal to e to the power of u, and u is equal to x squared. dy by du is just e to the u. Right, that's what we just saw on the last slide. And du by dx is equal to 2x. So we can put all of this back together to find dy by dx. So dy by dx, dy by dx is equal to dy by du, e to the power of u, times du by dx, which is 2x, giving us 2x e to the power of x squared. Now that was a whole lot of work, and we don't like doing extra work in maths if we can do things easily in our head and get it right. So let's have a look at how I can think about that now with the inside and the outside function. So the inside function is x squared, and the outside function is e to the power of a blob. So the derivative of this is just e to the power of the blob, because when I differentiate the exponential function, I get the exponential function, times the derivative of the inside function, which is 2x. So one more easy one before we get on to a harder one. If I've got y is equal to 4e to the 5x, then dy by dx is going to equal 4. My constant just gets multiplied through, so 4 times e to the 5x times the derivative of 5x, which is 5. That gives me 20 e to the 5x. Okay, let's look at some more interesting problems. I'm going to do all of them the same way, so I'm not going to write it out as u equals. If you want to do that and go more slowly, that's fine. Okay. Right, so where have the questions gone? Ah, the questions are back here. Okay, so the first one is very similar to the one that I've just done. What I want you to do though is, before I start going through them, can you pause the video and give all 6 of them a go? That'll take you a wee while, and then I'll work through them. Okay, so question 1, y equals negative 5 e to the 3x. dy by dx will be negative 5 times the derivative of this, which is 3 e to the 3x, and we'll clean that up as negative 15 e to the 3x. Right, question 2. Well, as soon as we see the surd, we know we need to change that to a fractional power. We have y equals 7e to the power of x to the power of a half. So I need to differentiate x to the power of a half. dy by dx is equal to 7 times the derivative of the inside function times the derivative of the exponential function, e to the power of what it was before. That gives me, I could probably get away with leaving it like that, but let's tidy it up. So we've got 7 over 2 root x e to the power of root x. Right, let's look at number 3. So number 3 is straightforward if you simplify it first, and that's often going to be the way with exponential work. So in all of these next ones, if we can remember negative powers easily, then they're not bad at all. Right, so number 3 can be rewritten as y equals e to the power of negative 3x. So it's now a very easy question. It's dy by dx is equal to negative 3 e to the negative 3x. Number 4 needs to be expanded. Well, I would definitely expand this first, right, because it's a very easy expansion just using our level, actually it's using a year 9 algebra. So 5 cubed is 125, and then here I multiply the powers. So it's 125e to the power of 6x. So dy by dx will equal 125 times the derivative of this, which is 6, times e to the power of 6x, giving me, I think, 750 e to the 6x. Now the next two came out of my OneNote equation editor a little bit funny, but what they're meant to be is e to the power of the thing. Might change pen colour. Let's see. Oh, don't like that. Yuck. Let's make it a bit thicker. So, what have we got? Y is equal to negative 3. Now, look what we've got here. This is e to the power of this, which looks really bad. So let's rewrite it as y equals negative 3 times e to the power of 1/5 x to the negative 3. Just be careful with that 1/5. So now I need to differentiate 1/5 of x to the power of negative 3, because that's my inside function. dy by dx will be negative 3 times negative 3/5 x to the negative 4 times e to the power of what we started with. Now that definitely needs a clean up. So it's going to give me here, writing it as nicely as possible, we get 9 over 5x to the power of 4 times e to the power of the thing we started out with. Get rid of that straight e. Okay, what's left? Oh, we're nearly finished. Right, number 6. So I thought I'd chuck one in just as the delta exercise does, that has some non-exponential stuff in there. Right, so we're going to rewrite it with negative powers. When I do that, I get y equals e to the power of x to the negative 2 minus x to the negative 2. So if you're watching this video and you're feeling even slightly uncomfortable about what I just did with negative powers, you need to go all the way back to level 2 algebra, go back to Education Perfect, and just make sure that you've got them really fluent, because you don't want that to be getting in your way. So dy by dx is going to equal the derivative of this, so negative 2x to the negative 3 times e to that power. And then here I'm going to have minus, differentiating this will give me negative 2x to the negative 3. So cleaning all that up, I get negative 2 over x cubed e to the 1 over x squared plus 2 over x cubed. There you go. Hopefully that helps. The next video that I do is going to be about differentiating the natural log function, which is a little bit harder than this one. That'll be sometime in the next week.